This video is about the paper I have been reading this week, which is it's called Logic Tensor Networks. And if I read the whole title, then it says Logic Tensor Networks, Deep Learning and Logical Reasoning from Data and Knowledge. So Logic Tensor Networks, LTN, and deep learning and logical reasoning. So it basically what it does, it combines deep learning and logical reasoning using from data and knowledge. So what it does is it basically integrates automatic learning that we already do using gradients and reasoning together. So you can learn using gradients that we do. So we can learn using gradients that we do in normal neural networks, and we can reason too. We can reason from what the neural network is learning along the way. Yeah, and they achieve this. So the main two contributions of this paper is one is the real logic, which is based on first order logic, and which simply put is representing the constants, the variables, the functions, the predicates, not all of them, but like the constants and the variables in a real vector, using a real vector. So let's say I have a constant which is let's say tiger, and you can represent this constant using a real vector of like size 3, and let's say so just to give you a quick example, like tiger, and this can be represented using 0 1 0, where 0 means, I don't know, it has 4 eyes, 1 means it has a tail, and this 0 means it has no parents, or something like that. So basically each and it necessarily doesn't need to be 0. I mean, it doesn't necessarily need to be binary. It can be decimal, it can be integers, it can be anything. So as long as it represents something, that's the idea of real logic, right? Okay, so so quickly going over the abstract, it says we propose logic tensor networks, a uniform framework for integrating automatic learning and reasoning. Logic formalism called real logic is defined on the first order logic, and there's a truth value involved, and semantics defined concretely on the domain of real numbers. Logic, and we show how real logic can be implemented. So yeah, the two contributions of the paper are real logic. Okay, I should write this. Real logic and implement real logic in TF. So the paper is written by Luciano Serafini and Arthur. I'm going to stop there because I know I'm going to pronounce it wrong. So I'm just going to stop there. Yeah, so excellent paper, by the way, like interesting, very interesting idea. And what this where this paper stands is in the field of neurosymbolic AI, where the idea is to integrate distributed representations with symbolic representations. Distributed representation with symbolic representations. So when so the idea is you can learn using the distributed representation. The idea of neurosymbolic AI is you can learn using the distributed representation, and one of the main problems, why neurosymbolic AI is coming into is like the next thing in deep learning is because like deep learning is kind of a black box, and you really cannot like reason why a certain model or a certain deep learning algorithm or a certain deep learning model is making a decision. Why is it making a decision, and what exactly is the reason behind it? So it cannot be said what is the reason behind it. So the idea is to integrate symbolic reasoning in the process, so we can tell the deep learning algorithm, and we actually have a clear route to as to how to reason with the algorithm. If we want to integrate something, or if we want to integrate reasoning, or if we want to integrate something inside it, we basically, it's a means of talking to the model, right? Yeah, that's basically what you're trying to do with symbolic representation. With as we're integrating symbolic representations inside deep learning, is that we're trying to talk to the model. Is that we cannot make it learn. We cannot make it learn, right? I mean, we can make it learn. So what I try to say over there is that we can write a deep learning algorithm. We can write a deep learning algorithm. Just a minute. So why deep learning came into place in the first place is basically we cannot write a logic program that differentiates between an apple and an orange. So we cannot tell the computer how exactly to differentiate between an apple and an orange. So we are still automating that process using deep learning, as we have done since the last 10 years. But now what we are trying to do is we're trying to have some control over what it learns, and some sense of reasoning, and some control over the reasoning of what it does and how it does it. Yeah, I think that's the best way to put it. Right. So yeah, so this paper is one of the approaches in the way in how to achieve neurosymbolic AI. What's the best way to perform neurosymbolic AI? There are multiple approaches, and this logic tensor network is one of the approaches. It builds on the idea of Guha's recent paper on model theory, which basically shows how to, which basically brings up the idea of representing of having a language based on first order logic, which can be represented using real tensors, right? And yeah, it does that, and this is one of the papers that it builds upon. And the other paper is the paper of neural tensor network, which is by Richard. Yeah, which is by, can you just say Richard? Richard, Danchi, Christopher, and Andrew from Stanford, I think. Yeah. So yeah, this is the reference number 26 of this paper. So this is what it's getting at. And yeah, let's see what it's trying to do. So ideally what this paper is trying to do, as I said, is it proposes a framework called the logic tensor network, and it integrates learning based on tensor networks on tensor networks, which is which basically is networks using tensors, I think. I'm not sure if I'm using, no, yeah, definitely, yeah. You know, when it says based on tensor networks, it means that, yeah, 26, that's Richard's paper. It means neural tensor networks. So with reasoning using first order many valued logic, and all implemented in TensorFlow, right? So this is what is basically the paper is trying to do. So, and it goes on blabbering some things. So given this enables for the first time a range of knowledge-based tasks using rich knowledge representation in the first order logic to be combined with efficient data-driven machine learning based on the manipulation of real valued vectors. Yeah, as I said, like real valued vectors, and given data available in the form of real valued vectors, logical soft and hard constraints and relations which apply to a certain subset. An adequate vector phased representation on the logic first proposed in this paper enables therefore of integration of learning and reasoning as detailed in what follows. Okay, so basically what it says is this. So it's basically saying we are proposing a framework called LTN, and which integrates learning based on neural tensor networks with reasoning using first order many valued logic. Okay, so we are interested in providing a computationally adequate approach to. Okay, so here it goes on defining the problem, right? How is the problem defined? So just a quick overview of the problem is like it says. So there's a set of objects, O, which is O equals O1. Sorry, O1 O2. There's a bunch of objects, and some of the objects are associated with a set of quantitative attributes represented by an n tuple of real numbers. So some of the objects are associated with a set of quantitative attributes by quantitative attributes. So this is the attribute. So each one of the objects has is composed of an n tuple of real numbers. So it's called grounding. So this is called grounding. So G of OI belongs to a vector of n dimensions. So for example, a person may have a grounding, so for 4 tuple grounding, right? So, and then object tuples can participate in a set of relations, right? So there can be a bunch of relations, object tuples can participate in those. So R1 to Rk, so there's a bunch of relations, and where Ri belongs to this, which where alpha is the arity, as in like how many terms the function takes. So let's say so I'm not sure what is O. O is the object. So which so this is like a subset of O. So let's say so alpha is the arity of the relation. So alpha, as in like, let's say the relation takes like three arguments, A, B, and C, or put it in the notation O1, O2, and O3, and the arity of the relation now becomes this. Let's say this is R2. Arity of R2 now becomes 3. So yeah, so whatever Ri is, it's the subset of that. It's a subset of that. Yeah, so Ri is a subset of the objects with that particular arity, and where alpha of Ri defines the arity of the relation Ri. We presuppose the existence of a latent relation between the above numerical properties, that is groundings, and a partial relational structure R on O. So skipping that's not important. Not very important. So C of X, classes and relations are not normally dependent. For example, classes and relations are not normally independent. So for example, it may be the case that if an object X is of class C of X, and it is related to another object Y, in logic of X. So mainly what it's saying is like for all of X there exists Y such that C of X, if X belongs to class C and there's a relation such that X is related to Y for some reason, then it also implies that object Y is of class C. So yeah, that's what it says right here. Okay, so otherwise there might not be enough. So whether or not C depends on the application, obviously. Let's say this is an example. So the above forms of reasoning and learning are integrated in a unifying framework. So all these all this reasoning. So basically, this reasoning that it currently shows, like for all X there exists and Y, such that if X belongs to class X, if X belongs to class C, and there's a relation between X and Y, then then Y also belongs to class C. So let's say this particular implication is not mentioned in the database, and then but it learns it, right? So if it says like there's an object X which belongs to class C, and there's an object and it's related to class Y, then it learns that object Y is also of class C, right? So that's what it's learning, and we can reason it with real logic. The idea is we can have a control over what it's learning, and we can have a control over we can have a say over what it's learning and how it's implying things and why it's implying things, and have a certain power of changing it. I'm not sure if it's possible with this with this, but the idea is like we have a power of changing it when it comes to if you want to change it. So that's the idea of the paper. So moving on to like this basically says how it's structured. Oops. How it's structured. Okay. So the idea of so next is the real logic which they introduce, and the idea of real logic is real logic is basically derived from first order logic. So they start with the first order logic and they have a bunch of constants and symbols, and basically the idea is they have a grounding to each one of these constants. So going over it quickly, they have there's a grounding G for a first order language is a function from the signature of L to the real numbers that satisfies the following conditions, blah blah blah. And so G of C is a constant. If C is a constant, then it is represented by n vector. So let's say if C is tiger and n is 3, then it's represented as 1 0 1, or anything else 2 3 5 or whatever. And let's say if f is a function which is like animal, where f is animal, and it's, let's say, tiger, and tiger name. So let's say this gives out the name or something, I don't know, something. So basically it returns a set of values. Let's say so actually ideally, let's say there's tiger, and let's say there is I don't know, something which returns okay, so let's say tiger and gender, and this returns male, right? So I mean, this is gender, this is tiger. Okay, so this returns male. So the idea is tiger, which is represented by 101, takes this goes into this gender, and this male comes up, which is also represented by a three-dimensional vector or whatever the size of n is, and let's say that is like 5 6 1, right? This is random numbers. And the idea is, so what it says over here is g of f it belongs to Rn dot alpha of f. So where alpha of f is the arity of the function f. So let's say the function takes one parameter. So so for this particular function the arity is 1. So R of n is dot 1, which is n. But in case like the arity is 2, then it's not 2n, it's still n. As you can see, it's basically, the idea is like, let's say there's some function which takes two arguments, argument 1 and argument 2. Then the result is in a way whatever the result is, result 1, this is in a way combination of two vectors. So let's two n vectors, right? So in a way that's n dot 2, but the representation is ultimately of n, right? So ultimately it's Rn. Okay, so yeah, that's the idea. And g of p, if p is a predicate, that's where animal comes in actually. Animal of tiger, and it says yes, it is. Instead of yes, it will say 1. So it belongs to 0 and 1 real numbers. So for p every p, and a grounding G is inductively extended to all the closed terms and clauses as follows. So let's say what is the grounding? This particular example. So this particular thing over here. Wow. So this particular, oh my god. Okay, this particular thing over here. Yeah, so let's say there's a grounding, and this grounding is on f, which takes, the arity of f is m, and this is the same as the grounding of this particular thing will be the same as the grounding of the function, which when applied to the grounding of each individual terms. So that's what it says. That's what all these things say. So the same thing applied to all of these. And the last one is a bit different, which is basically saying ki, let's say ki the grounding is applied to phi of phi 1 or phi 2 to phi k. So I think phi is phi is a clause. Yeah, phi is a closed clause. Phi is a closed clause. So let's say ki it's it basically is a, I can't remember the term, but it basically is a sentence, kind of like or, and whatever the grounding is of the whole thing, it will be the whatever the value is of the whole thing. So whatever the value is of the whole thing, it's new, which is an S norm operator, which as I'm thinking is a columnized norm operator. It's columnized normal form, and which belongs to G of which will be basically the same thing when the S norm operator is applied over the grounding of each one of these closed clauses, right? So yeah. Alright, so this is a quick example which says, like, let's say there is a bunch of objects, O1, O2, O3, and there's this sentences, then there's these sentences, where are the sentences? Okay, yeah, so this is O1, O2, and O3, so this is a bunch of sentences, and this is what they are represented as, the groundings of each sentence, and this is the word, this is the dictionary. So basically the grounding is represented as if this word is present in the sentence, then it's 1, otherwise it's 0. So, and then there's this function which is f. So you can see concat of the function, so it's g1 or g of o1 plus g of o2, and this gives a n-dimensional vector which is same as this. And this is a sim. Okay, the sim is basically a predicate which basically says how similar the two sentences are. So it concats these two sentences and then compares it to O3. So then there's a cosine, I think this is a cosine similarity, so which gives us a 0.18 value, which it shows the key as same as the two things apply differently, which is also it's kind of similar, 0.866. So yeah. So that defines real logic. And next is learning as an approximate satisfiability, which is basically how real logic is going to be how they're leveraging real logic into to formulate it into a learning equation. So basically kind of the loss function. So how do you how does one leverage real logic to learn from that, right? And when there is language involved, there is a notion of satisfiability, and that's where that's what it means when it says learning as an approximate satisfiability. Now it's hard to like pinpoint what exactly is satisfiability, like what is satisfiability, but then one can always define a satisfiability, and like it's always kind of an approximate satisfiability. So the three definitions over here is one is the three definitions are the satisfiability, what does it mean for something to be satisfied, what is a grounded theory, and what is a how is a grounded theory satisfied. So satisfiability is phi be a closed clause, phi be a closed clause, and phi b, and G a grounding, and yeah. So given that, so if phi is a closed clause and G is a grounding, then the satisfiability of for the closed clause for that particular grounding is defined as this, which is which basically says that given the grounding, so given the closed clause, the grounding should be in the interval of v2 omega. So a partial grounding, then G cap is a grounding that is defined in a subset of the signature. A grounded theory is a set of clauses in the language L. A grounded theory is a set of clauses in the language L and partial grounding. Okay. So grounded theory, so that is satisfiability, and the grounded theory is defined as a pair where where K and G cap. So G cap is the partial grounding, and K is a set of pairs like this, where phi of x is a closed clause again, containing x of free variables, which takes x free variables, and the value for that is a subset of 0 and 1, is a subset which lies in the interval of 0 and 1. So yeah, and yeah, that's a partial grounding. So given this grounded theory and satisfiability, how do you say, how does one say like a grounded theory is satisfied? So so a grounded theory is satisfiable if this is the case. So which is given everything, so this is the idea. So given the grounding and the phi cap, so given a grounded theory which is G cap, there exists a grounding which extends G cap. So given G cap, there exists a grounding in the space, in the complete space G. Is it there here? No, not here. In the complete grounding space G, there should be a grounding value which extends G cap such that for all the closed clauses and its free variables, it lies in the interval of v2 omega. So ideally what it's trying to do is ideally to find such a grounding. So given a partial grounding, to find the space of all possible groundings, that's one challenge, and the instantiations of all these closed clauses and whatever vectors there are, like instantiations, so like you try all the instantiation. So it's not practical to do that. And how does the paper approach it? How does the paper approach it? So searching within the specific class of functions. So basically what it means is it assigns a vector over here, and it searches in that, it assigns a tensor and it searches in that tensor kind of. So it says in particular, we are interested in searching within a specific class of functions in this paper based on the tensor networks. So although the family of functions can be considered, but it's not, because, and to limit the number of instantiations, infinite sense L admits function, the usual approach is to consider the instantiation of each clause up to a certain depth 3. So when a grounded theory KG is inconsistent, that is, there is no grounding G and satisfies it, we are interested in finding a grounding which satisfies as much as possible of KG. We want to find a grounding that minimizes the satisfiability error, obviously, and assigns G cap. So loss is defined something like this, where given a grounding and given a K, X is the predicted value for the satisfiability, and G of that closed clause is the true value, and it's the difference between that. So yeah. Okay. Oops. Okay. So if G cap is in the interval of V cap, then the loss is 0. So yeah, if G cap is in that, then loss is 0. So if the above definition, now we can call what is a approximate satisfiability. So given a grounded theory and a finite subset of the instantiate. So given a grounded theory and the finite subset of I of the clauses in K, where K0 is a subset of, it basically says these are the I, and if G is the grounding of family of grounding functions, we define the best satisfiability problem as a problem that extends finding an extension G star of G cap in G, and that minimizes the satisfiability error on the set of K0. K0 is the instantiations, that is G star, G star is the minimum given the loss, and given k naught, given k naught and given loss, the v omega of vt, phi of t is like given a k which belongs to k naught, the particular I, one particular I, and which sums over all particular i's. So we are finding the I which is the minimum, and summing over all the i's, calculating the loss, and we are trying to get a G star, G cap, which is a subset of G and belongs to the grounding. Yeah, that's what it's trying to minimize. That is satisfiability error. And given this update function, now given this update function, now I have to implement implement real logic in tensor networks, right? So that becomes more of the equation, equation 2. So W, V, and BP are and as well as U are the parameters which the network learns, and W is basically is the tensor for each predicate, for each function, for every relation. Basically, there is a tensor. There is a separate tensor, so there is a separate neural network for every one of these every one of the terms. So given a relation R, let's say we're trying to say given given a predicate which is, let's say, animal, there's a tensor dot. So there's a depth of k, and it's m cross n, mn cross mn tensor, and each slice, the interpretation is like, yeah, the intuition is each slice represents is the transformation or the weight or what the vector is learning, or what the network is learning for that particular property of the grounding of the clause or constant, anything. So vt of w, vt and v, which is vt is the transpose. So v is the f is a function symbol of arity m, and v is defined as v1 to vm, which belongs to n. Each one of which belongs to n are real vectors corresponding to the grounding m of terms this and this. So v is basically the grounding of whatever there is, and it's this particular is a bilinear interpolation, is a bilinear, not sure if it's called bilinear interpolation. So wp of 1 is to k v, which is the 3D tensor is of r mn mn k, and this is a single layer. This part is similar to what a normal neural network does, which is that there's a single layer, there's a single matrix transformation, and this is the bias. Yeah, okay, right. And yeah, so this particular thing where vt wp1 k vt is rk, this is rmn, so let's just call it dk, and this is rk. So given each slice, for each slice this gets multiplied with this. So in a way mn is actually So ideally the whole thing comes down to RK. I've done this calculation. I'm not going into details. The whole thing comes down to RK. So each one of it is RK, and then finally after applying sigmoid, we get a number which ideally should be between V and omega, and then if it's not, it's compared. The loss is applied with this, and the whole operation happens. Okay, so I'm going to just rub this thing. Okay, so. This is how it looks. Like, this is a nice example of how it looks. It's you have V, you have U, and then you can go into details with this. It's this TH is the tan H. This is the sigmoid function. Okay. So this is an example of knowledge completion, and it's applied on the friends and smokers example. So there's two groups, A, B, and H, A, B to H, and I, J to N. Who has and does not have we have a complete knowledge of who has and does not have cancer in the first group. And second group, this is not known for any of the person. Knowledge. Within each group, we have complete knowledge of their smoking habits, but we don't know who has cancer, and knowledge about the person. So that's basically the idea. So given that this is the knowledge base defined, like who has cancer, and who has smoking habit, who is a friend. So S is the smoking habit, F is who is a friend of whom, and C is whether the person has cancer or not. After applying the logic tensor network approach, this is the table that reasons out. So they do two experiments. One is there's some difference between the two experiments. I'm not going into details. So it has some initialize. It initializes by for one experiment it initializes with some knowledge, and the other one it doesn't. So anyway, the point is it learns about the thing. So I think yeah. So the cancer habits, cancer is not known for who has cancer is not known in group 2. This is group 2. So you can see, like, this starts with if I'm not completely wrong, table 2, figure 2, table. So the results of the second experiment show that facts can be learned with the inclusion of background knowledge. So there's some background knowledge. Given in result in the experiment 2, and so its degrees as well higher than 60%. CI and CN cancerous to CI and CN. So for CI and CN, it didn't know. The knowledge base didn't have the information whether it has cancer or not. But after learning, it says it has cancer with a high prediction probability. And this is the smoker information. So since these values also increase because these are friends of some smoker friends, and their chances of having cancer also increases. So that's the idea. So even the knowledge information is even if the knowledge information was not there, even the knowledge base didn't contain that particular information, it still somehow managed to learn it, not somehow, because of the real logic and its particular implementation. It learned about the smoking habits, the smoke that other people are exposed to, and the chances of people having cancer. Yeah. So after that, it continues with some related work, which is basically 15 is Guha's paper, Markov logic tensor networks, blog, Bayesian logic. 25 is, I don't know what is 25. Check. And 11 is something. It's also a nice paper. And 10 is neural network fibering. So yeah, these are the two contributions. Main contributions of the paper was real logic and implementation of real logic in TF, and it basically showed what is real logic, which is basically defining a grounding for each one of the things you have in the language. For the signatures of the language, you define a grounding for each one of them. Now this grounding can be a vector, provided what is given. If it's a function, it's a vector. Given it's a constant, it's a vector. Given it's a predicate, it becomes a value between 0 and 1. And then satisfiability is the comparison, is the satisfiability of this, of what the value is. And satisfiability is what the value is, and based on this satisfiability and given a grounded theory, we try to extend, we try to compare the particular values and define a loss function. And then there's a neural tensor network which is defined, then there's a neural tensor network which is defined for each one of the predicates, and each one of the predicates and the constants, and this particular tensor is being learned over time, and this particular equation 2 is basically the main equation of this paper, which shows, but it's not a contribution of this paper. This particular equation is contributed by 26, which is Richard et al.'s paper, which basically introduces neural tensor network. So it shows shows how to how basically the neural tensor network learns. And yeah, that's it. All right, that's it. Cool.